Today we're going to talk about B trees. B trees are self-balancing tree data structures that keep data sorted, allow searches, sequential access, and insertions and deletions in logarithmic time. Nodes can have more than two children. B trees keep keys in sorted order for sequential traversing and uses a hierarchical index to minimize the number of disk reads. So I wanted to go over an example of a B tree. In this example, we see three keys in the root, which are 4, 10, and 16. Because it has three keys, you know that it's going to have three keys. The four children nodes are 1, 2, 3, 6, 7, 9, 11, 12, 15, and finally 17, 22, and 36. B trees use partially full blocks to speed insertions and deletions. They also keep the index balanced with an elegant recursive algorithm and minimize waste by making sure the interior nodes are at least half full. A B tree can handle any arbitrary number of insertions and deletions. The B tree is optimized for systems that read and write large blocks of data. Basically, the main thing is that accessing disk is much slower than memory access. One disk access takes around 8 milliseconds, which is about the same as executing 200,000 CPU instructions. Because of that, it is definitely worth executing lots of instructions to avoid a single disk access. Because accessing disk is so slow, data on a disk is stored in blocks of size B. A typical block size is between 1024 bytes and 8192 bytes, and the whole block is read per one disk access. In searching a tree, accessing each node most likely will require reading that node from the disk. The larger the tree height, the more disk accesses we need. Using a B tree with high branching requires smaller number of disk accesses, assuming a tree node fits into one disk block, which is why B trees are so great to use.
B trees is a very popular data structure. Its well-known uses in databases and file systems. B trees' internal nodes can have a variable number of child nodes within some predefined range. When data is inserted or removed from a node, the number of child nodes changes. The lower and upper bounds on the number of child nodes are typically fixed for a particular implementation. Each internal node of a B tree will contain a number of keys.
Let's take a look at how the B tree insert operation works. We'll do this by building a B tree from scratch of minimum order 3. We're going to take the sequence of 14 integers presented here to be processed as keys for our B tree. Let's look at the first element of our sequence, 21. Because no B tree has been initialized yet, we can default the assignment of 21 to the root node. Given that this B tree is of order 3, we know that a node can have a maximum of 5 keys. This means that the next 4 elements in our sequence can be assigned to the root node. 13, 25, 28, and 77. We now examine 92. 92 happens to be the largest element in our sequence so far, and we have dotted all the space in our root node. This means that we have to split the root from the median. process of inserting 92 into the B tree is as follows. We begin at the root node and traverse down to the white subtree. We have to check this node for additional space, and we find that there is space for insertion. All we do now is simply insert 92. We now process 89. Again, we're traversing down to the white subtree, and we can see that there are a total of 3 keys in this node. We still have 2 additional spaces left over, so we can go ahead and simply insert 89. Following 89, we Following 89, we're to process 98. Again, we traverse down to the white subtree, and following the last available for 92. Following 89, we're to process 98. Again, we traverse down to the white subtree, and following the last available position with 98. At this point, we are to insert 32. This time, however, we are traversing to the white subtree again, only to find an overflowed node. This calls on a procedure called merge or split child at the median, 89, which will merge in with the parent. Now, at this point, we see that the middle pointer located right here directs us to the proper node where 32 is to be inserted. We check for additional space and find that we can insert 32 right in between. Now we are to process 12. This time we are actually going to traverse down to the left subtree as 12 is less than 25 and insert it right before 13. We move on to element 29. 29 means that from the root node we are traversing to the middle node to check for additional space and proceed by inserting it into its proper position. We are now at element 17. We traverse down to the left node, check for additional space, yes, and insert it right here. This brings us to 66. 66 calls on us to traverse down from the root node to the middle node. Here we have a node with 4 elements, so we have 1 additional position available for 66. Our final element is 3. We start at the root node, traverse down to the left side. Our final element is 3. We start at the root node, traverse down to the left subtree, and insert 3 in its proper position. At this point, you can ascertain that we have kept the properties of a minimum order 3 B tree. Any node had at most 5 elements, 5 keys, and a minimum of 2 elements. We also check and see that the root node had a total of 3 children. B tree insert, as mentioned before, is a logarithmic algorithm and thus runs in all log of n time. B trees delete is a bit more involved and complex than insertion in that there are a variety of cases for which delete occurs. Each of these cases depending on the location of the key, we have to account for different rebalancing acts so that we maintain the integrity of our B tree. The first example, and the most straightforward one, is to delete a key from one of the leaf nodes. In this case, we can elect to delete 15, 16, 19, or 20, all on level 2. When we delete one of these keys, let's say we delete in 16, all we do is delete the key from the node and maintain the current key in the node itself. There's no rebalancing to adjust for the deletion of a key from a leaf node. On the other hand, deletion of a key from an internal node means that we have to examine the predecessor and successor elements, which are found in this case in the left subtree and right subtree, to borrow from or merge depending on the ordering of the keys in relation to the subtrees. In the case of 21, we see that its predecessor is in its right subtree, so we choose to delete 21 and instead we replace it with 20. You can see that in this fashion, the order of the keys is maintained. If on the other hand, we were to delete 17, it has both its predecessor and successor elements in the right and left subtrees. This means that when we delete 17, we shift the 21 over to its position and have this pointer to the left subtree be a pointer to the merged. The result of merging the predecessor and the successor elements into one node. Again, this maintains the relation between all the keys in the left subtree.
The B tree represents a generalized form of the binary search tree. In binary search trees, each parent node stores one key. B tree nodes, by contrast, contain a number of keys whose range is defined as a function of the order of the tree. Binary search trees have a constant number of children for each parent node. For B trees, the number of children is only limited by the number of keys in the parent. Because a range of child nodes is permitted, B trees do not need rebalancing as frequently as other self-balancing search trees. B trees have substantial advantages over alternative implementations when the time to access the data of a node greatly exceeds the time spent processing that data. Because the cost of accessing the node may amortize over multiple operations within the node. This usually occurs when the node data is in secondary storage such as disk drive. The only major disadvantage of a B tree is it may waste some space because nodes are not entirely full.